Good morning, and thank you for attending this webinar. My name is Mike Lawless, and it is my pleasure to discuss the physicochemical and biopharmaceutical module of ADMET Predictor. The goal of in silico ADMET modeling is to accurately predict ADMET properties based solely on the structure of the molecule. This slide illustrates the linkage between QSPR predicted properties and gastrointestinal simulation. A drug that is orally delivered will typically dissolve in the stomach, where the pH can be as low as 1.4. It will diffuse into the small intestine, where it is absorbed via the enterocyte cells into the portal vein. The portal vein then delivers the compound to the liver. Portions of the compound that are not metabolized in the liver make it into systemic circulation. Biopharmaceutical properties such as permeability, solubility, diffusivity, pKa, log P and log D, among others, can be used to parameterize simulation of gastrointestinal dissolution, transit, and absorption. This talk will focus on prediction of these physicochemical properties. This next slide is an outline of the talk. First, I'll present an overview of the physicochemical and biopharmaceutical module. Then I'll discuss our model building procedure. This will be followed by some literature examples where the researchers have compared our predictions and others. In the fourth section, I'll discuss our multiprotic pKa prediction module. Then I'll talk about our log P and log D models, followed by predicting water solubility and other related properties. And then in the final section, I'll discuss absorption risk, which is an absorption liability score. This slide shows all of our predicted properties within the physicochemical and biopharmaceutical module. In the upper left-hand corner, we start with the pKa model, which is a multiprotic model with complete microspeciation. We have a diffusion coefficient model. For lipophilicity, we have two log P models and a log D model, which allows you to predict log D at user-specified pH. We have several permeability models, starting out with our human effective permeability in the jejunum. We have an MDCK apparent permeability model, two models for blood-brain barrier penetration, a corneal permeability model, which would be used maybe to model compounds that are delivered as eye drops. We have a skin permeability model, which would be applicable for creams or patches. We have an OATP1B1 inhibition model. Several models related to solubility. Our native solubility model also allows you to compute or predict the native pH at saturation, intrinsic solubility, salt solubility factor, solubility at the user-specified pH. Then we have several models for simulated in vivo gastric fluids, both fasted and fed states, supersaturation ratio model, several models for pharmacokinetics such as human plasma protein binding as percent unbound, volume of distribution, and blood to plasma concentration ratio. We have a Henry's law constant, which is the measure of a gas air partition coefficient, and then a couple of activity models. So let's just pop into ADMET Predictor. So here I've read in structure file containing 16 compounds that were approved by the FDA last year, and they're all orally bioavailable drug molecules. So I'll just go down to the calculate properties, click on that button to predict the properties of all the molecules, and then we can go into the biopharmaceutical module and start looking at the various properties we predict there.
Our Moriguchi's log P and our own S log P, which is an artificial neural network model, log D, then PEF. So here we have the permeability, models MDCK, corneal permeability, skin permeation. Then we have our water solubility and related models. So here's the native water solubility, solubility, or the pH, native pH of the saturated solution, intrinsic solubility, salt solubility factor, and then this is the solubility at the specified pH, which was input here as 7.4. These next three models are for simulated gastric fluids, and so we commissioned Northeastern University in Boston to test about 160 drug-like compounds in various gastric simulated fluids. So they had various pHs. One was a low pH that would simulate the solution in the stomach, and then others were various percents of things like chlorocholate, sodium hydroxide, sodium chloride, HCl, and then various pHs. Then over to the far right, we have our tendency of a compound to supersaturate in water. This is a classification model, and basically it's going to be true or false. Next, we have our blood-brain barrier models. So we have a classification model that indicates whether the compound is likely to cross the blood-brain barrier. And so for this third compound, Belvig, it does have to penetrate the brain, and we do predict that its tendency is high to penetrate the brain. The next column is the partition coefficient between the blood and the brain, so the tendency for the compound to prefer to be in the brain over the blood. The percent unbound, so this would be plasma protein binding in the form of percent unbound. Volume distribution, the S plus RBP model is the tendency of the compound to, it's the ratio of the whole blood to plasma concentration, and also indicates how much of the compound goes into the red blood cells, or is partitioned in red blood cells rather than plasma. You'll notice that for this top compound, the prediction is colored magenta, and that indicates that the descriptors, or at least one of the descriptors for this compound, is outside the applicability domain of the model. Next, we have the OATP1B1 model, which is a classification model, just yes or no. And then finally, a couple of HIV activity models, and then over to the far left, or far right, we have absorption risk and absorption code, and I'll talk about those in the last section of the webinar. Okay, so going back to the slides, this slide illustrates our model building procedure for artificial neural network models. So it's a general slide to illustrate basically a flow chart of model building procedure. So we start out with structures and experimental data, and we take a great deal of care in curating the data and making sure that the structures are in the appropriate form and that the experimental data is correct. So we'll go back into the original references, pull those up, and make sure that that data is correct. If you don't have good data, you're not going to have a good model. Next, we compute a large number of descriptors. We have over 300 descriptors currently in the program, and they're broken up into these 6 classes. So constitutional is just what the components of the molecule, topological, hydrogen bonding, ionization, which also looks at a pKa model, electrotopological, and then finally charge and reactivity, which I'll discuss during the webinar, but these basically come out of some EEM and Huckel molecular orbital calculations. So now you can think of the data in a spreadsheet form where the rows are the molecules. We have a column for the property we're trying to predict, and then the other columns will be the descriptors of the molecule, both atomic and molecular descriptors. The first thing we do is remove descriptors that don't vary from row to row. And if they don't vary from row to row, they're not going to be any good in describing the variation in the property. We also do a pairwise correlation of all the descriptors and remove descriptors, or if two descriptors are highly correlated, we'll remove one of those descriptors to avoid redundancy in the descriptor space. Next thing is to create a test set. There are various methods listed here to create the test set. The key point is that we sequester the test set and it's never used in training, and we also do not cross-validate. So this is truly an external test set. The other molecules not in the test set will go into a training pool. Now, a priori, we don't know what models, what number of neurons and number of descriptors are going to create the best model, so we perform experiments where we create a large number of models with different architectures, i.e. different number of neurons and descriptors. And we have a method called several different sensitivity analysis methods to try and pick the best descriptors for the various architectures. Once the model is trained, we apply it to the test set and then bring the results back into a grid where the rows are the number of neurons and the columns are the number of descriptors, or excuse me, number of descriptors. Then we have algorithms for an algorithm to select the best ensemble, but we also rely on the modeler's intuition. And then finally, we'll select a single model that is an artificial neural network ensemble. So it's actually 33 artificial neural networks, and typically we would average the output of this of these to come out with the final prediction for the molecule. Okay, this next slide really speaks to our model building procedure and our descriptors. So this is a paper that was published in 2008 called the Solubility Challenge. It was published in the Journal of Chemical Information and Modeling. And basically the group performed experiments on 132 compounds where they measured the intrinsic solubility of each compound. And then in the publication, they released the structures and intrinsic solubility for 100 of the compounds. The other 32 compounds, they just listed the structure. And they challenged modelers to take the 100 compounds, develop models based on the 100 compounds in the data, and then use those models to predict the intrinsic solubility of the other 32 compounds. We submitted 8 models from Simulations Plus, and the 8 models ranked in the top 12 out of the 100 submissions, and that was published in 2009. And so that just speaks to our model building procedure and the descriptors used in the models, and illustrates that we create really good models with ADNet modeling. Moving on to the next section, we've had a number of publications from independent researchers showing that our QSPR models are the best in class according to these publications. First publication came out in 2003 in this book cited down here. It was by Dearden, and he looked at various log P packages and then measured, ranked them according to the percent of compounds at various error ranges. So QMPR plus used to be the name of the ADNet predictor. So it ranked first with 94.2% of the compounds being predicted with an error of less than half a log. This next slide is the second independent comparison of log P predictions. It was published by TETCO in 2007, and ranks our S plus log P model. Incidentally, if you see S plus, that stands for Simulations Plus. So our log P model ranked number 1. The author ranked it as a tie with A log P S, which incidentally is TETCO's program. And you see, though, that we did do much better on the Zwirr ion than the A log PS. This next slide shows third independent comparison of log P predictions. This was published by Manhold in 2008 and shows our log P performance on a very large data set of about 96,000 compounds. It also included a data set called Nicomed that included 882 compounds. You see again the S plus log P model ranked number one, again with the tie A log P ranking. This is a consensus model of multiple models here, so we'll go with that one now. If we look specifically at the percent of molecules within the error ranks, you can see that actually we do have a higher percent with the lower errors than the A log PS method. Also, I want to indicate that there are two models here for Moriguchi log P. One uses simulations plus descriptors, and the other uses dragon descriptors. And if both of these had calculated the descriptors the same, then both would have had the same RMSE and rankings. But the fact that the dragon descriptors ended up dead last indicates maybe there's something incorrect in some of those descriptors there. Then the fourth comparison here is for solubility. This was from Dearden's article in 2006, where they compared simulations plus and a number of other modeling packages. And again, we came out on top for solubility, which is a difficult physicochemical property to predict. Okay. Now moving on to the next section to discuss our predictions of multiprotic ionization constants. I just again want to state that if you have multiprotic ionization in a particular molecule, it's very difficult to predict these from structure alone. And I think you'll appreciate that as we go on through here. Why is pKa so important? Well, it affects a large number of other properties. Such as lipophilicity, solubility, permeability, metabolism, and transport, just to name a few. There are obviously other properties. So it's important to have an accurate pKa model as a prerequisite to achieving accuracy in many other models. So let's take the case of cetirizine. This is a well-studied molecule. It contains three ionizable groups. So we have the carboxylic acid group, we have an aliphatic amine in this pyrazine ring, and notice that this aliphatic amine is closer to the two phenyl groups. And then finally, another aliphatic amine that's the other nitrogen in the pyrazine ring. So the macroscopic apparent pKa's have been determined in a usual titration experiment, and the values are 2.1, 3.01, and 8.17. And that's from this publication down here in 2009. So the tendency, and what's also taught in colleges, is to assign each one of these pKa values to a particular group. And that's a bit erroneous because you really have multiple states at any one of these, contributing to any one of these apparent pKa's. So the complexity is really illustrated on this next slide. So let's start on the right side of the figure in the completely deprotonated cetirizine, highlighted here in red. So we have no protons on here, and we want to add a proton to this corresponding as the pH is raised in the experiment. So where should this hydrogen go? So there's three places it could go. It could go on the carboxylic acid, it could go on the nitrogen closest to the phenyl rings, or it could go on the one distal from the phenyl rings. And the tendency, of course, is to say, okay, this pK is associated with one of these particular microstates. But in reality, all three of these have been observed in solution, and so they all contribute to the apparent pKa. Similarly, if we move over here a bit to the left, we have two protons to add, and they can go in two of the three positions on the molecule. So either the carboxylic acid and one of the pyrazines, carboxylic acid, the other pyrazine, or the two pyrazine nitrogens. And then finally, in the completely protonated form, there's no ambiguity here. So overall, we have 8 ionization microstates. That's computed by 2 to the n, so we have 3 ionizable groups, so 2 to the 3 is 8, and we have 12 microconstants, and these are the numbers between the microstates. So this is a microstate and a microconstant. And our challenge with the model is to predict the microstates populations and the microconstants, all from the apparent pKa's. So how do we go about doing this? So we have a number of molecules in a training set, and this just illustrates the simplified mechanics of pKa modeling. So we take this compound and we calculate a large number of atomic descriptors for the ionizable group in the molecule. Using QSAR, we compute the micro pKa's. So maybe the first question is, what are atomic descriptors? And here are examples of just 4 atomic descriptors. Here we have E states, electrotopological states, EEM plus Huckel total charges. And these were calculated from our Huckel molecular orbital model. We also have Huckel pi free valences and Glenn polarizabilities, just as examples of atomic descriptors. So the overall ADMET predictor calculates about 140 different descriptors per atom in a molecule, and these are excellent for predicting localized properties such as pKa and sites of metabolism. So we had a grant where we parameterized this EEM and Huckel molecular orbital theory to predict ab initio partial charges. So we had a large number of molecules. We ran through ab initio calculations and then parameterized our EEM Huckel method to reproduce these charges. And as you can see, our model does an excellent job of reproducing the ab initio charges in a fraction of the time. So the RMSE for the training set is 48 1,000s, 41 9,000s for the RMSE of the test set. And again, a large number of atoms were used to parameterize the method. Okay. So kind of putting this all together and applying it back to cetirizine, so we would have a training set, and for each one of the training sets, or excuse me, for each one of the ionizable groups in the training set, we would develop artificial neural network ensemble models, and then combine that with microequilibrium theories from the predicted microconstants to calculate the apparent pKa's for each of the molecules. Overall, we had almost 14,000 ionization macroconstants from about 11,000 organic compounds that was from a database purchased from BioBite. We divided the molecules into 10 subsets according to the dominant group being ionized. So for acids, we had hydroxy acids, acidic amines, aromatic NHs, thioacids, and carboacids. For bases, amines, aromatic nitrogens, and oxides, thiones, and carbobases. Then an artificial neural network ensemble was generated for each of these 10 groups up here, and then they were combined together with a comprehensive optimization of all the ensembles simultaneously within the realm of the microequilibrium theory. This next slide shows how our model does. So these are the observed pKa's and the predicted pKa's along the x-axis. In the training set, we had about 10,000 pKa's and 3,500 for the test set. And as you can see, we have a very low RMS of 0.56 for the training set and 0.587 for the test set. So let me just pop again into ADMET Predictor and show our predictions on cetirizine and how the program performs. So we're going to calculate physicochemical properties for the molecule, and then simply click on the gray button here. This will illustrate the various microstates in here. Now, one thing we note here is that we're only computing microstates that contribute more than 1%. And as you see for this microstate here, the one that's missing is the one that just has the proton on the carboxylic acid. And so that doesn't actually show up in greater than 1% population here. We also, so along this column is the pKa for the transition between the macro states. So at the top we have the completely deprotonated compound, then we're adding sequential protons to the molecule for the various macro states. And then you can also see the percent contributions of the microstate to the macrostate. So for the neutral compound with one proton, 96% is predicted to be protonated in the piperazine distal from the phenyl rings, and then a smaller percent on the one that's closest to the phenyl rings. For the positively charged macrostate, you get contributions from 3 different microstates, both where the carboxylic acid is protonated along with one of the 2 piperazines, and then this state where both the piperazine nitrogens are protonated, and then finally the completely protonated species. We can turn on the micro constants to examine the micro constants between the microstates, and then we can also show related graphs. So this particular graph shows all the microstates for the compound, and we can turn on or off various graphs. Clicking on this button here will scroll through different different graphs. So in this one, we're only displaying the macro states. We can move this bar along here and then hit the space bar and get an indication of the fraction ionized for this particular compound. So it's saying that at 7.52, 71.56% of the molecule is in this particular macrostate, the neutral macrostate. We can also plot, make Bergeron plots, which are the number of protons versus pH for this particular molecule. So let's also briefly take a look at some of the FDA compounds here. Again, go into the stage here. So for this particular compound, we have a number of different protonation states, +2 all the way varying to the -1. We can use this to scroll through the various ones. So this next compound is acidic, so at pHs between about 5 and 10, it's mostly in the negatively charged form. And then we have a simple basic compound that at biological pHs would be completely protonated. Okay, and then just one final statement on our models in the macrostates. For cetirizine, the microstate proportions for the positively charged species is shown here in an experiment performed in 2001, and we can compare that to those predicted by ADMET Predictor. And you see that we agree that this state is the highest percent, but then for the other 2, our rank is reversed relative to the experiment. So from the experiment, they say that this is the next highest population, where we say that this state over here is the next highest population. These experiments were performed again with newer techniques in 2009 and then published in 2009. And here you see that ADMET Predictor now is in agreement with this particular experiment as far as the rank ordering of the predictions. And this is something we've seen before in that we have a prediction and it might disagree with the experiment, but then later on newer experiments are performed or and published in the literature, and we see that our model was correct all along. This next section describes our log P and log D models in the ADMET Predictor. So our log P model was built an artificial neural network ensemble based on almost 13,000 compounds selected from an error-corrected BioByte master file. So we purchased the data from BioByte. Here's the publication on that. And we did do some curation, found that there were some incorrect structures and data, and then we looked back in the original publications and corrected that. So our model was built on ion-corrected experimental log P values. Again, we have the observed versus predicted log P. For the test set, we had 1,200 compounds, and for the training set, almost 11,000 compounds in there. And again, we get excellent root mean square errors for the training and test set of about 0.3. So with log P, you're just looking at the unionized proportions of the molecule in the octanol in water. If you want to consider pH-dependent distribution, you need to look at the log D. So log Ds need to be measured at a specific pH. And so we developed an ADMET predictor model based on partition coefficients for charge forms that are calculated directly from structure, not just an adjusted pH, log P, excuse me. So we're trying to predict this delta of the charge forms. So we consider 3 charge forms: anionic, cationic, and zwitterionic, and then users can specify the pH for the log D prediction. This next slide shows the observed versus predicted log P. Again, we have a very large training set and test set, 6,500 compounds in the training set and about 2,200 in the test set. And the RMSE for this is slightly higher in the than the log P model of about 0.56 for the training set and 0.539 for the test set. In this section, I'll discuss our water solubility and related models. This slide illustrates different methods for measuring solubility. The first method is native solubility, and this is really the best one for modeling. It is the equilibrium thermodynamic in pure water, and it lets the final pH depends upon the saturation concentration of the molecule, in other words, how soluble the molecule is, but also what its pKa values are. The next method illustrated here is solubility in buffers. This is best for salts. Again, we get an equilibrium distribution, but here we're using a buffer, so it's at a known pH. And the molecule can be anywhere from 0 to 100% ionized. And finally, we have HTS turbidity assays. This is precipitation of the molecule from an organic solvent by adding a pH 7 buffer, but it only provides rank ordering of the solubilities. This slide illustrates the problems with trying to model solubility from data collected at a fixed pH. So along the y-axis, we have the solubility in milligrams per milliliter, and then along the x-axis, the pH for these two particular molecules. Note that they both have a protonatable amine contained in the molecule. So if we were to obtain the solubilities at a pH of 2, these two molecules would have very similar solubilities. If we obtain the pH at closer to 7.4, you see that these two have very different pHs. Now, this really makes it impossible to measure or to model because the descriptors are going to be the same for the model, yet we're trying to come up with two different predictions for each one of these molecules at different pHs. And so what we model is the native water solubility, and this is quickly illustrated on this slide. So we have a flask of just pure water, so there's no buffers, no salts, etc. And then the compound is added to the water, and again, this is in its pure form. It's not a salt, and then you just keep adding, shaking the flask until equilibrium concentration is reached at room temperature, and this is known as the native solubility. So we obtained a data set of solubilities and used those to create an artificial neural network ensemble, and the results of that ensemble are shown here. So in the training set, we have about 2,700 compounds. In the test set, roughly 900. The root mean square error for the training set is 0.607, and for the test set, 0.562. So once we have a native water solubility model, we can derive different other property predictions from that native water solubility model. So the next one is the native pH. So it's the equilibrium pH at saturation. It's calculated from the native solubility and our ionization constants from our pKa model. Intrinsic solubility is also predicted. This is for the neutral species only, calculated from the native solubility, native pH, and ionization constants. And then finally, we have the solubility at a specific pH. Again, this is calculated from this one's calculated from the intrinsic solubility, salt solubility factors, and ionization constants. Okay, so let's go back into ADMET Predictor and just compare a couple of compounds and their predictions at different pHs. So I'll calculate these two compounds' properties at 7.4. And then resize the screen just a little bit and bring in another version of ADMET Predictor and bring in the same two molecules. This time when I calculate the properties, I'm going to change the default pH to a lower value of 2 and go ahead and calculate the properties at this pH. So we have two predictions, one at 7.4 and the other at 2, and then we'll display those top and bottom. So the top one is calculated at pH 7, and so we'll just quickly go over here to our log P and log D predictions. This compound here has an acidic group. Its log P is 2.4. The log D at pH 7.4 is 0.69. So it's in an ionic form here, and I'll just quickly bring up the macro states for this compound. So as you can see, when we graph the macro states for the acid and go up to pH 7.4, that most of the molecule is in its deprotonated form, as shown by this graph. Okay, for the other compound, this is a basic compound. The log P and log D are about the same according to our predictions. Now let's take a look at these predictions at a pH of 2. So we go over to the log D. Here you see on the bottom that for the acid at pH 2, the log D and log P are the same. And the reason is that most of this compound is in its neutral form at pH of 2. For the base, log P and log D are different because this is mostly in its ionized form. And again, we can look at its graph down here at 2. Again, clicking the space bar, making that a little bit larger. And you see that 90% of the molecules predicted to be in the +3 charge form for this particular molecule. Let's also look at the water solubility prediction. So this is the native water solubility prediction. It's not going to depend upon pH. We have the pH of equilibrium, so 4.27 for the acid, 8.49 for the base. Then if we look at the solubility at pH 7.4, that's listed here. So for the acid at 7.4, it's mostly deprotonated, and so its solubility is very high, 14 milligrams per milliliter compared to the native solubility. So once this compound goes into the stomach, it's going, and when it's neutral, the pH is very high. If we look down here at pH 2, which could be the pH in the stomach, you'll see that the predicted solubility for this compound is much lower now at pH 2. If we look at the basic compound at 7.4, it's 0.02 milligrams per milliliter. If we look at pH 2, now it goes up to 9 milligrams, and again, because it's in its ionized form, which is more soluble than the neutral form. Switching back to the slides and presenting the last section, which is absorption risk. This is an absorption liability score. Absorption risk is a subset of a bigger risk score called ADMET risk. ADMET risk is a flexible scoring system. It has many components to measure the liability risk of a compound, such as absorption risk, metabolism risk, and toxicity risks. These rules are customizable, so you can remove rules or add some of your own rules. By default, we provide 24 default rules. The rules are based on property value estimates of a qualified subset of the World Drug Index. We took about 2,300 orally delivered compounds from the World Drug Index. We measured various predicted various properties for these compounds, and then applied thresholds such that 90% of the compounds would pass these thresholds. In other words, they wouldn't be assigned a liability score. So it's an easy way for a chemist to rapidly measure the compound in many dimensions with a single number. Each one of the risks are augmented by 2-letter codes to identify which rules are violated. And this can be used in early design and discovery in order to filter large candidates of molecules. The ADMET risk has 4 components. The first one is the absorption risk, which I'll discuss in detail in the following slides. The metabolism risk is basically a score indicating that either the compound might have a high metabolic clearance, which is bad for a drug molecule, or it might inhibit cytochrome P450, and this may cause drug-drug interactions. For toxicity risk, we look at hERG liability, rat toxicity, carcinogenicity in mice and rats, liver injury, and antimutagenicity. And then finally, we have 2 other properties which aren't associated with specific risks, but are counted in the ADMET risk. One is a low fraction unbound in plasma, so this is a fraction unbound, and then a high steady state volume of distribution. And if you have a high volume of distribution, this may indicate that the molecule is going into the tissues rather than being available at the therapeutic site in cells, etc. ADMET risk is based on size, flexibility, hydrogen bond donors, acceptors, excessive charge, lipophilicity, permeability, and solubility. So this slide illustrates how we would set an individual threshold. So we took the subset of the World Drug Index, calculated its log P values, and you see the distribution graphed here of the log D, and then we set a threshold such that 90% of the compounds, as illustrated by these blue bars, would pass that threshold. And what it ends up is the S plus volume of distribution ends up being greater than 5.5. So if a molecule's volume of distribution is predicted to be 10, then there would be a flag set for volume of distribution and would be given a code of VD. This next slide shows a chart of the various properties we look at for the absorption risk. So one is the size, and indicated by high molecular weight or large number of atoms or bonds or a high molecular volume. We also have a penalty for too many excessive rotatable bonds, too many hydrogen bond donors and acceptors, excessive charge. This is calculated from a natural population analysis based on our Huckel molecular orbital calculations in EEM, and then lipophilicity, too high octanol water partition coefficient, low permeability, and then also low solubility would be flagged as a liability. So in conclusion, a compound's absorption potential requires accurate estimates of key physicochemical and biopharmaceutical properties, and most of these properties are significantly affected by ionization. ADMET predictors, log P and solubility models have been ranked #1 by independent researchers. For multiprotic species, the experimentally observed pKa can be due to multiple microspecies rather than a single group. And this is really an important take-home lesson. Colleges are still teaching that one pKa should be assigned to a specific functional group, and that's really not true. It involves multiple microspecies. We predict native water solubility, and this can be used in combination with the pKa values to compute other properties. And then finally, absorption risk is a measure of compounds. Absorption liability, it's a flexible scoring system that can be changed by the user. And then finally, I'd like to acknowledge my coworkers. Dr. Robert Franskiewicz really understands pKa and built the models. Bob Clark is our Director of Life Sciences. Dr. Shengjing Hua submitted the solubility models. Marvin Waldman does the log P and log D. And then finally, our CEO of Simulations Plus is Walter Woltoff. And I'd like to thank everyone for listening, and I think we'll welcome any comments or questions. So we have other panelists on board, Bob Clark and Robert Franskiewicz also. So Robert, I'll maybe turn it back over to you for any questions.
Yes, thank you very much, Michael. Those were very nice presentations. We have a couple of questions that came up during your presentation, and I will be happy to answer them in the order received. I will answer both in writing and also directly to the whole audience. I hope everybody can hear me. The first question was from James Kress. Any calculation for permeability of cell nucleus membrane or prediction of diffusion coefficient across this membrane? This is the membrane between a nucleus and cytoplasm. So thank you very much for bringing this to our attention. This particular endpoint has escaped our attention before. The short answer to this question is not yet. There are a lot of questions about different endpoints that different users are interested in, and all of them have essentially the same answer. Our modeling capacity is only limited by the quantity and quality of the available experimental data. The priority which a particular endpoint receives is also heavily weighed by the number of inquiries from current and prospective users. So this question definitely brings this endpoint to our attention, and if James is very much interested, I encourage him to contact us directly, and we'll talk about it. The next question was from Jack Jones. Are the slides of this presentation going to be available? Yes, the slides will be available to everybody. After this presentation, all the attendees will receive an email with appropriate links. The next question was also from James. I think it pertained to the part in which Michael was talking about ADMET modeler. Can we choose descriptors for modeling? Yes, absolutely. We can selectively turn descriptors on and off, and as an added bonus, users can also import their own descriptors if they choose so. At one point, Michael was talking about our government-funded work on ab initio charges, and the question was which ab initio charges did we use? These were charges calculated at the density functional theory level using 6311G double star basis set. This is for those who are familiar with quantum chemistry, and B3 LYP functional. These calculations were processed through natural population analysis, and the resulting charges were used as training set. Next question from Li Zhao. Which software should we use to draw the chemical structures? For example, ChemDraw. And is specific format required for ADMET to read? Yes, we definitely recommend our own software called MedChem Designer, and I think Michael will show the ADMET predictor. Will open one of the structures. MedChem Designer.
Yes, so MedChem Designer is a free software package, a drawing software package that you can download from our website. So just go to our website, and it's integrated with our various products. For example, I'm showing ADMET Predictor here. I can hold down the Shift button and click on the structure, and that brings up ADMET Predictor. MedChem Designer. With MedChem Designer, you could modify this structure and then send it back to ADMET Predictor. If you thought the structure was wrong or you wanted to do predictions on a different structure, we also have a yellow button here that will perform the predictions on the molecule here. We can also copy that molecule and then maybe modify it. So let's take this hydroxyl group and make it a methoxy group. Click on the AP button again and get the predictions for the methylated compound. And as you can see here, the log P goes from 2.54 to 3 with the methyl group on it. The log D goes from 0.65 or 685 to 3. And this is simply because this is no longer available for deprotonation. So I'd highly recommend just downloading MedChem Studio, MedChem Designer, and we also provide a few of the ADMET Predictor properties with it. To get all this list, we have to have a valid ADMET Predictor license.
Mm-hmm. That's correct. I may also add that free version of MedChem Designer has also built-in S+log P, S+log D at pH 7.4 models. For descriptors, topological polar surface area, molecular weight, hydrogen bond donor and acceptor capacity, as well as Geiger's sigma charges. So it all comes free with no cost. And the second part of the question was about specific formats. The following formats are accepted by Victor: SMILES, MDL's SDF, RDF, the particular mole format, which is actually part of SDF and RDF formats. I listed it under the names of subsequent companies that were taking over MDL. It was first produced or designed by MDL, which was acquired by Symix, which in turn was acquired by Acceleris. And finally, the TRIPE or Certara format called MAC, which is essentially the same as MOL. Next question. This is.
And I just want to say that.
Go ahead.
I just wanted to say that I've got the list there on the screen. So the 2D can be SMILES, SDF, RDF, and MDL. Sorry about that, Robert.
No problem.
To you.
So the next portion of questions came recently. I didn't have time to type the answer, unfortunately, so I'll just answer orally. Jonathan Vesey asked, are the predicted values dependent on the tautomer that the compound is represented as? Yes, they are. Currently, they are dependent on the specific tautomer form. Nevertheless, this is when I will announce our future developments. The next version of ADMET Predictor, namely 7.0, I'm sorry, 8.0, is going to have a feature that will make the predictions independent of which tautomer was submitted. That I think we see it as a very important development. Next question was, how can we transfer the PK data to Gastro for further calculations? I will also elicit Michael's help. Michael, can you open ADMET Predictor and show the safe option for Gastro plus acid base table? So yes, we have two compounds with calculated properties, and Michael, this really came too fast. Can you cancel that and open it?
Oh, okay.
Slower because there's a delay.
So file.
Transferring the video.
Okay.
So it is in File, Save. It's still updating. Okay, it's there. A Gastro plus acid base table. Here you go. So that will open a specific options window, which will let the user to choose which properties will go into acid base table, either predicted PKs or imported from outside. For example, you may have experimental PKs that, for some compounds, but not for the others, and you can mix them with actually predicted PKs. The produced tablet delimited text file is then importable by GastroPlus. Next question is
Mike, Robert, hang on a second. Robert?
Yes?
Also, if you're in GastroPlus and you import a structure and you have either the AP module of GastroPlus or an ADMET Predictor license, it will call ADMET Predictor and load the PKA properties into your property K file.
That is correct, yes. The Gastro...
You never ever actually have to launch ADMET Predictor.
You're absolutely right. GastroPlus has its own module which can call ADMET Predictor directly. That is correct. Okay. Next question is quite interesting, and I will also need Michael's help. Are there any predictive capabilities for chemical transport across cell membranes via transporter proteins? for the determination of metabolism and clearance values. And yes, we do have a couple of transporter models. Michael himself built the model of OATP 1B1 transport, and he will show it to you in a second. This is the transport across the hepatic cell membrane. This particular model actually talks about transporter inhibition. Which version of unmeasured predictor do you have?
Yeah, it's not the latest one, so
Okay.
we should have a PGP model too.
Exactly. In the latest version of unmeasured predictor, we have also a model of PGP efflux. This is actually a seed of a new module, which we will call in the future transporter module, which will be populated with various transporter transporter protein-dependent models. We will make it this set of models available as a separate module. Rebecca Vito asks whether the ADMET predictor is free or do we have to buy a subscription. Well, in general, this is a subscription-based program. Nevertheless, the evaluation version is free. You can get the program to evaluate for a limited amount of time. I think it's 2 weeks. But Anu Sharma will answer this question in more detail. Now, James has clarified the question about descriptors. He asked whether the descriptor descriptor removal. During modeling, he wants to automatically remove descriptors during pairwise correlation screen. And can we choose at that point which descriptor ADMET removes? ADMET predictor, ADMET model removes the descriptor according to the order in which the descriptor appears. So you're right. If two descriptors are pairwise correlated, the order in which they remove this is simply semi-random. In order to prevent it, you can explicitly remove one of the correlated descriptors prior to modeling. So I would advise to build a little short model in the beginning to quickly discover which descriptors are correlated, and you can view it in the log file, and then decide which descriptors should go in and which should be removed, and simply manually remove the ones that you don't want. So next question is really interesting. Can the software offer suggestions to improve ADMET properties, like change some of derivatives based on its database? Actually, we have something even better. Yes, you can load a database of different derivatives and compare predicted properties and simply get an intuition on how the property changes with structure. But we can also offer another thing, and Michael will show a descriptor sensitivity analysis where a specific property can be examined in more detail from the molecular descriptor point of view. So while the window is opening, let me say that sensitivities are calculated for regression properties, for example, log P, now shown by Michael, as specific gradients with respect to specific descriptors. So for example, for the first compound, the sensitivity with respect to the the first descriptor, okay, and which has a cryptic title NPA-AQON. This is actually sum of partial atomic charges on oxygens and nitrogens. The sum of absolute values of partial atomic charges. So simply this descriptor is telling you how charged are nitrogens and oxygens. And as expected, the log p value has a negative sensitivity with respect to the descriptor. So the more charges you have on these particular atoms, the smaller the log p. If Michael clicks on the sensitivity line now, this can be seen as a continuous curve that shows dependence of predicted log p on this particular descriptor, while all other descriptors are kept fixed. So the specific set of examples is available in ADMET Predictor tutorial as well as on our website on how to use this feature, which is really powerful, to design new molecules with desired properties. Hong Wang asks about how to reload saved.csk file to ADMET Predictor. So it sounds cryptic. CSK is an internal format used by Metchem Designer. ADMET Predictor does not read CSK files directly. They are very specific to Metchem Designer. These are structured drawing files for those who ever used Metchem Designer. Nevertheless, Metchem Designer enables a user to select structures that should be opened by ADMET Predictor and either calculate them directly inside the program or export them in one of the formats that is readable by ADMET Predictor, like, for example, SMILES, SDF, or MOLD. So there are multiple ways of doing that. Michael is showing right now how to draw a structure and export it as SMILES input file, which can be then read by ADMET Predictor. Yes, James asked another question about descriptors. There was no mention of 3D descriptors or 3D QSERs. The 3D QSER can be understood in terms of what I would call traditional 3D QSER. For example, something akin to COMPA analysis and so on. So ADMET Predictor does not do that. Nevertheless, ADMET Predictor has a set of 35 of 3D descriptors, which depend on three-dimensional structures of molecules. These three-dimensional descriptors can be calculated and used in the usual QSER sense. So these descriptors are automatically turned on when the program receives three-dimensional input. Sirisha asks,
can I make a...
Go ahead.
I'd like to make a comment on the 3D. This is Bob Clark. I spent a lot of years before coming to Simulations Plus working with 3D descriptors and working in 3D models. And one aspect of it is for many of the models, the kinds of models, the kinds of data and properties that we're trying to model in ADMET Predictor, 3D modeling really doesn't work very well. Even in the cases where it might, like for cytochrome P450s, by the nature of things, they're acting on a lot of different kinds of substrates, and they tend to have extremely flexible binding sites. So they're almost all cases, and transporters are the same thing, almost all cases where 3D techniques really don't work very well because the ligand specificity is too broad and the binding sites are just too flexible, or there are too many different binding sites contributing, for example, for mutagenicity.
That is
Thanks,
correct.
Robert.
No problem. The next question is, what additional data does the 3D structure give us when compared to the 2D structure? Well, it's a very broad question and can be answered multiple ways. In terms of Android predictor, I would say not much. There is only a limited set of Android predictor models where the use of 3D descriptors makes a real difference. And in all these cases, the difference is really small. One of the examples is, for example, water solubility. A 3D version of our water solubility model is slightly more accurate than 2D version, okay? But the difference is really, really small. And it's intuitively understandable. Water solubility depends on two major factors, mainly on solvation and also on crystal lattice energy. Solvation part can be exemplified or can be calculated in 2D sense. I'm saying it because our S+ loop model in its 2D and 3 is indistinguishable in terms of accuracy from its 3D version. So 3D descriptors really don't matter that much for lipophilicity. It's a property that can be modeled by 2D descriptors alone. The crystal lattice energy is actually more complicated than that, and probably does require the insight into 3D arrangement of atoms of a molecule. This explains why 3D descriptors matter in this case. I hope that answers the question. And finally, the last question was, can you explain more how to use the risk factor assessment? We use different ADMET risk scores, essentially, to filter out molecules. I'm not sure if you heard about it, but last year we have announced a discovery of 8 new truly novel anti-malarial compounds. We did it entirely from the public data released by GSK, and we designed these molecules entirely in silico using ADMET predictor as well as NetChem Studio software. Details of it can be found on our website, and if you have more questions, don't hesitate to ask. Bob Clark was the primary investigator of this project. We have truly proven the concept that novel drugs essentially can be entirely designed in silico. There's one more question coming up. Can we upload PDB files in case we want to calculate other properties of peptides as drug molecules? Well, you can calculate properties of small peptides, okay, to the extent at which they were included in our training sets. Android predictor is truly software for small molecules. It will not, it will process molecules up to 256 bonds. This is how we limit the size of molecules. So that includes very small peptides. It's really an arbitrary limit that can be changed in the code. but changing it wouldn't amount to much because we really don't have larger peptides in our training sets. So even though it's theoretically possible to process those molecules and calculate descriptors and so on, I don't think the predictions would matter too much because they are really not represented in the training sets. So it is likely that large peptides will be outside the applicability domains of our models. And James pointed out that yes, the specific PDB format is not read by an predictor, but can be converted to any of the formats readable by the program using for example, free tools such as OpenBabel. That, I think, concludes our question section. If there are more questions or comments, please voice them now. Go ahead, Michael.
Yeah, I just want to turn it back over to Anu. She wants to say a few closing words on the webinar.
Thank you, Michael. Yes, my name is Anu, and I'm the manager with sales and marketing. We offer 2 weeks of free trial license. If you're interested in trying out, I highly recommend you take advantage of this opportunity. For Admet Predictor and Metcon Studio, you can reach me. My email address is on the screen. And if you're interested in consultancy services, Michael Lawless is the person responsible. So you can contact Michael at the email address as shown. And if you're interested in trying out GastroPlus or the DDB Plus, then please contact John Videla again. I will be following up with you. All these emails are going to be in the last slide of the slide deck, so please don't hesitate to reach us anytime. And we also exhibit at the various upcoming conferences. Another place where you can meet with us is at the KCO PDS meeting in Foster City. This is a local meeting, so for all the California attendees, you may visit our booth and see our products. And we will also be at the Zinc conference. This is a medicinal chemistry conference. This is a conference we are sponsoring, so we will be giving a talk there as well as we will have a booth. And it's a beautiful place, Napa Valley, to be in for the summer. So if you're attending, please stop by, and another place to connect with us. And for our attendees in Japan, we are organizing a workshop on GastroPlus in October. The information for the registration is on our website. And again, this is a great opportunity to learn about the GastroPlus, and which will also have some Admet Predictor training as well. So if you have any questions, please don't hesitate to reach any one of us. I will be following up with all the attendees in the email. And again, we appreciate your time and your attention. Thank you so much.